Now that we've understood accuracy, precision, and recall used to evaluate classifiers, let's now talk about how we can apply these metrics to evaluate our classifier to find the best model for our use case. Here is our classification model, which tries to determine whether a whale is a fish or a mammal. We've fed in information: a whale breathes like a mammal, gives birth like a mammal, and it's correctly predicted that the whale is a mammal. Though we talk in terms of predicted labels at the output of your classifier is actually a probability score. Let's say the probability scores at the output of this model are in terms of the probability of the input instance being a fish. For a whale, this probability score is 0.45. It's below the 50% threshold, which is why it's categorized the whale as a mammal. Let's go back to our coordinate axis, one that we are familiar with. On the y-axis, we have the probability of the animal being a fish. And on the x-axis, we have the features that we feed in for every animal. Let's say that the features that you feed in are that this animal lives on land, breathes with lungs, does not lay eggs. The probability of it being fish is just 5%. On the other hand, along this S curve, you might have other data points. Let's say you feed in information such as this animal lives in the water, breathes with lungs, does not lay eggs. The probability of it being fish are higher, maybe from 40 to 60%. And finally, at the very top of this S curve, you have the following features. This animal lives in the water, breathes with gills, and lays eggs. The probability of it being fish is 95%. Now, along this curve, whales, are they fish or mammals? Now, in order to determine this, what you need to define here is a threshold along which you'll categorize an animal as a fish or a mammal. This threshold could be 50% or could be any other value that you decide. Whatever the P threshold, this is what you use to categorize your input. If you get a probability output from your model which is less than P threshold, you'll say that that animal is a mammal. Or if the probability score, that is the output of your model, is greater than P threshold, you'll categorize that animal as a fish. Let's now consider different threshold values to see the effect on your model. If P threshold were equal to 0, that is an always positive classifier. So if you have a threshold of 0, your model will always say the patient has cancer. Let's see how a threshold value of 0 affects your model. Now, the recall of such a model is 100%. All cancer patients in your dataset will be correctly identified. The precision of your model, though, is really poor. It's just 13.7%. This classifier is said to be not conservative enough. It's basically tagging everyone as having cancer. It's not really a good model. The less conservative your classifier, lower the precision. Let's plot a curve of conservativeness of your decision threshold along the x-axis and the precision of your model along the y-axis. You'll get an S curve like you see here on screen. As your classifier becomes less conservative, precision falls. As your classifier becomes more conservative, the precision will increase. Let's now consider a classifier at the other extreme. This is an always negative classifier. This classifier has P threshold equal to 1. It always flags no cancer. As you might imagine, the metrics of such a classifier are likely to be skewed in a different direction. This classifier will have a recall of 0%. It will not categorize or find any cancer patients. On the other hand, the precision of this classifier is infinite. This classifier is way too conservative. Now, if you plot the conservativeness of the decision threshold versus the recall of your model, you'll find an inverted S like you see here on screen. A classifier that is way too conservative in detecting cancer will have a recall of 0. The two S curves that we just looked at, precision and recall versus the conservativeness of decision threshold, shows you that there is a trade-off involved here. If you try to tweak the decision threshold to increase the precision of your model, recall will fall and vice versa. So if you take precision versus recall with precision on the y-axis and recall on the x, you'll get a curve that looks like this. Higher recall means lower precision, lower recall means higher precision. Well, if that's the case, how do we find a model that's good for us? How do we choose the right value of P threshold? There are several heuristics that you can use. The one that we'll discuss here is the ROC curve, or the receiver operating characteristic. On the y-axis here, we have the true positive rate, the positive predictions of our model that are correct. And on the x-axis, we have the false positive rate, the positive predictions of our model that are incorrect. For a good classification model, we want the true positive rate to be as high as possible. That's pretty obvious. In addition, we want the false positive rate to be as low as possible. Once again, pretty obvious. This curve that we'll draw here, true positive rate versus false positive rate, is the ROC curve, or the receiver operating characteristic. So how do we get this curve, and how will that help us determine the right value of P threshold? Well, for different values of P threshold, plot the true positive rate versus the false positive rate. This is hyperparameter tuning. You'll tweak the values of P threshold and see how your model performs. You'll plot the true positive rate versus the false positive rate, and you'll fit an ROC curve for different values of P threshold. Now that you have this ROC curve, this will help you find the right value of P threshold. Pick the top left corner point as P threshold. At the top left corner, you have that value for threshold, which maximizes the true positives in your model and minimizes the false positives. This is how the ROC curve will help you find the right decision threshold and the best possible model for your data.